All right, this is the continuation of the 10.5 notes to finish up the normal distribution discussion. Just to recap, we learned how to compute a z-score, which kind of is a nice way to take any raw data where we have an item and a mean and a standard deviation, and we can convert that to its position on the bell curve, where these numbers, kind of -3 to 3, tell you if you are so many standard deviations above or below the mean. Now, in class, we practice converting some data values into their z-score. And we learned that our table for our class, which is again provided on your exam, you don't have to memorize all these numbers. It only reads the area from 0 to your z-score. So that can be either positive direction or negative direction, but it only can read from 0 to a z-score. So all these little decimal numbers here. So let's say my z-score is, let me just draw a secondary picture. Let me say that my z-score came out to 0.89. Okay, and let's say I wanted to know the area between 0 and 0.89. So you would find 0.8 on the column here, your z column, and the second decimal point is 9, so we need to find 0.09. If you put these two together, that makes 0.89. So 0.8 and 0.09 make 0.89. If you find where those two things overlap, that is the area or probability that someone would be between the mean and that z-score. Okay, so that's what that value gives us. So just kind of recap, that's how you read the table. Now we did one example where we then had something where maybe we wanted the tail at the end instead of the area between. And I'm going to show you again some more examples with that in this video so you can see how to practice that. We will also end this section with a discussion on how to use the normal distribution to approximate the binomial distribution. Instead of having to do all of those big formulas we did today with this ncx, p to the x, and q to the n minus x, if your distribution or your number of trials is large enough, you can actually do it by approximating it with the normal distribution. So that'll be where we end our discussion for today. All right, so let's get back to the notes and look at the next example that we had not done together. So let's talk about this one right here. So just to recap, this example said that salespeople for a medical device company have an average annual sales, so that's their mean, of 500,000. Let me zoom out a little bit so you can see that. So that's the mean with a standard deviation of 20,000. Now this one says, what is the probability? So we're looking for probability. That's like area. It's that decimal value we were looking at on the table, that the salespeople would be expected to make a sale of 485,000 or more. So we're looking for the z-score related to 485,000 or more, which means we are going to infinity essentially. Okay. So our item of question is 485,000. Our mean was 500,000. Standard deviation was 20,000. If we work out the top and then divide by 20,000, you're going to get a z-score of negative 0.75. Now, visually, what that would look like is when you're at 0 and you go down to negative 0.75, you're actually going below the mean. Now, we want the area to the right of that or more. So this is actually two separate areas. We have the area between 0 and negative 0.75. And then we have the area above that 0 mark. That's its own area because remember, our table only tells us 0 to a z-score. But the nice thing about the normal distribution is we already know that blue area. When you have the mean in the middle, which is 0, the area to the left or right, if you shade the whole thing, that's a 0.5. So we just need to look up on the table. We're going to look on the table to find this yellow area. So let's go to our table. And remember, there's no negatives on your table. That's because the area from 0 to positive z is the same thing symmetrically as 0 to the negative z of that same value. So we're looking for 0.7 and 0.05 because that'd be 0.75. Find where those overlap. That is at 0.2734. Okay, so I'm going to put that back on so this is 0.2734. That's that yellow area. Now, so if we want to make 485,000 in sales or more, we have to take the negative 0.75 to 0 area. That was the z-score, and then up to the mean, and then the 0 to infinity area, and we need to add those together. So the probability that my z-score is greater than or equal to that negative 0.75 is the 0.2734 plus the 0.5 for that other complete half, or 0.7734. So there's my probability. Okay. Probability and area are interchangeable words. So just remember, sometimes I'll say area, sometimes I'll say probability. Area is kind of the visualization of me shading it in, but the areas represent the probabilities. Okay. All right, let's look at another one. It says the average healing time of a certain type of incision is 240 hours. So that's our mean because they said it was our average. So I like to label those things with a standard deviation of 20 hours. Okay. What percentage? So this time we have to be careful. They're asking for percentage. That does need to be noted that that's slightly different than probability or area. Probability or area, you use the decimals from the table. Percentage, you still use the decimals from the table, but you turn it into a percent at the end. So you times by 100. And then we add a percent symbol. So they're saying what percentage of people having this type of incision would heal in 8 days or less. Now there's a problem with this. Days is not the same thing as hours. So the first thing I need to do is convert to hours so that we match with our mean and our standard deviation, because otherwise this isn't in the same units. So remember, there are 24 hours in a day times 8 days. That is going to be 192 hours. Okay. So we're doing the z-score of 192. So that's our item, minus the mean, which is 240, over the standard deviation, which was 20 hours. So notice everything is in hours. If you subtract the top and then divide by 20, you get negative 2.4, comes out exactly to that. Now be careful, this is or less. So if you draw a picture, it's always helpful to draw the picture. We put our mean of 0 in the middle. Z-score this time is to the negative direction, so negative 2.4. And then we want to know the probability of, or the percentage, which is tied to the probability of it being less than 8 days. So less than the 192 or the negative 2.4. So we're actually looking for this area. So when you're looking for a tail, remember the table is going to give you this. It's going to tell you 0 to negative 2.4. So we will need to do the fact that the whole half over here is 0.5. We're going to need to do 0.5 minus the table value to find that tail. Okay. So let's go and look up 2.4. This is, again, it doesn't matter if it's positive or negative as long as you're measuring from 0. Those are symmetrical areas. So 2.40, so that would be the first column, is 0.4918. So this is 0.4918 for that in between negative 2.4 to 0. That's that area. So 0.5 minus 0.4918 equals 0.0082. Now, if I was saying what's the probability or what's the area, I would leave it like this. But because they want it as a percentage, times that by 100%, and it would be 0.82%, because timesing by 100% just moves your decimal 2 places to the right. Okay, let's look at this next type. It says, given a normal distribution with a mean of 100 and a standard deviation of 10, find the number of standard deviations. This is from the mean. Standard deviations from the mean just tell me the z-score, okay? The z-score is a manifestation or a representation of that position in reference to 0, the mean, okay? So we're saying we kind of take any raw data and we make the mean 0. That's what that formula we've been using does. And then all of the other values we get tell us how many standard deviations either above or below the mean we are, depending on if they're positive or negative. So if I take this raw score and say 134, that's the item, minus the mean for the group, which is 100, divided by the standard deviation, this is going to come out to 3.4, because you get 34 divided by 10. So what this means is we are 3.4 standard deviations above, since it's positive, the mean. If we'd gotten a negative z-score, we would say we are that many standard deviations below the mean. Okay. All right, now look at this one. It says consider the normal distribution with a mean of 80 and a standard deviation of 5. Find the area under, so notice they're asking area, which means decimal, under the normal curve and above the interval 82 to infinity. So notice they're telling us how to do it. Instead of saying greater than or equal to 82, They're saying we're going from 82 to forever, essentially. So we're doing a tail. So we need to first take 82 and convert it to a z-score. So 82 minus the mean for the group, which is 80, divided by 5. That's going to give me a z-score of 0.4. So if you imagine drawing that as a picture on your bell curve, zero's in the middle. 0.4 would be just a little bit to the right of that. And we are looking for the area above that to infinity. So we're going from our z-score of 0.4 to infinity. Because remember, 82 and 0.4 are both representing the same place on the bell curve. This just allows us to use our table, okay? So when we look up our table value, remember, we're going to get this in the table. We're going to find the area between 0 and 0.4, and then we'll have to subtract, remember, 0.5 minus the table value is how you get a tail that goes to the infinities. Okay, so 0.4, let's look that up. So it's going to be a little higher. And notice it had no second decimal place. So if you don't have a second decimal place in your z-score, you're in that first column with a 0 there. So that's going to be 0.1554. So this table value right here is 0.1554. So that means the area in the pink is 50% or half of the bell curve minus the area in between 0 and 0.4. And that's going to be 0.3446. And again, I don't need to convert it to a percent because they ask for the area. So only time we convert to a percent is if they say, what is the percentage? Okay, a couple more, and then we're going to talk, the rest of this video is just to talk you through how to take what we learned in 10.4 about binomial distributions and when are we allowed to use the normal distribution to help us get a approximation for the binomial without having to do all the formulas over and over again. Okay, so that's going to be the final goal. But before we do that, here's this last example. Find the area under the normal curve from 0 to 3.2. So they're already telling you they are in the standard normal curve. That means these are the z-scores. This is z of 0 and z of 3.2. So this is just directly reading off the chart from 0 to 3.2. Remember, I draw the 3.2 far out because 3 is almost at the very edge of the tail before it heads towards the infinity. Okay, so we need to just look this up. It's directly from the table. So 3.2 and 0, remember that is exactly what the table tells us. That's 0.4993. So this one is 0.4993. Okay, so it's an exact table reading. This one says the area under their standard normal curve from the interval of 1.24 to infinity. So we already have they already told you it's standard normal. That means -3 to 3. So these are z-scores. This one's just to infinity. So this is from that z-score forever. So here's about 1.24 roughly. I just eyeball it where I think it would be. And then we want to shade to infinity this time. So we're going from here to forever. And again, you still use your table, but your table is only going to tell you 0 to 1.24. So we'll have to do 0.5 minus the table value when we're doing a tail that goes towards infinity. Now I do say it's that way. You do have to remember, we did do one where the tail was going to infinity, but we had to break our answer into 2 parts. Just reminding you of this. That's because we crossed the mean. So if you're doing a tail to infinity, but you're crossing your mean, you do technically have 2 separate areas you need to calculate. When your tail is only on one side of the 0, that's when you use the 0.5 minus the table values, just to make that distinction for you. So if we look up our table value of 1.24, let me erase some of these other ones. So I have 1.2 is this row, and I'm supposed to have a 0.0 or 4 for the second decimal place. So 1.24 is 0.3925. So 0.5 minus 0.3925. And since they wanted that as an area, we just need to write that in decimal form. That is 0.1075. Okay, so that ends the first part of 10.5 where we're just using the z-score formula and learning how to read the table to find different probabilities or areas. Now, let's talk a little bit about why we want to use this method of z-scores to help us do some of the binomial distribution stuff. And we only can do it in specific cases. You can't just always use the normal distribution for any binomial distribution. There have to be enough trials, and the probabilities kind of have to work out in a certain way. And I'll show you a rule in just a minute of when can we use it. Okay. So for a probability distribution of a continuous random variable, the probability of x assuming a single value is always 0. So in other words, if they say what's the probability of being actually a specific number, that is 0. We are doing the probability of a discrete random variable assuming a single value is usually a positive number between 0 and 1. So because when we do continuous variables, we're not doing a single value. Notice we're shading a region. We're actually, to find a probability, we have to be looking at a continuous set of numbers. Okay. So that's just the difference between what we were doing before, where we were just doing a single probability, and these are kind of on a continuum. All right, so approximating a binomial distribution with a normal distribution. When a binomial random variable assumes very large numbers of values, the probability distribution formula, which we learned in the last section, 10.4, which was probability of x successes in n trials, that was n choose x. Remember, that was how many trials I have, choose the number of successes I want. Probability of success happens x number of times. Probability of failure happens all the other number of trials. So if you have 100 trials and you have 5 successes, you'd have 95 failures. Okay. If you have 100 trials, you don't want to have to work with that many big number, like all that big stuff in the formula, especially if you need to do, if you have 100 trials and you want to know what's the probability that at least 20 of them were successful. That's every number from 20 to 100. That's a lot of different calculations for that formula. That's why we say if it's a really large number of values, it's going to become tedious. An appropriately selected normal distribution can simplify the computations and give good approximations to the probability binomial distribution formula. The following examples outline normal distribution approximations of binomial distributions with relatively small n's and with a large value of n. So we just want to talk about this so you can see it. Now, the big thing you have to be careful of, and I'm going to show you visually why we have to do this on the next page, is something called continuity correction. When we shift from a binomial distribution to a normal distribution, we must make 0.5 or half step adjustments. The reason for this is in a binomial distribution, remember each number of successes had a histogram bar. It had a bar that was a width of 1 and half of the bar was on either side of our number. Okay, we talked about that when we were drawing the histogram. So when you do a normal curve, every single value is a single line straight up and down on the curve. So because we're going to be dealing with going from bar graph kind of histogram width to a single line, we need to make those half step adjustments. So I kind of write it out here. It says, if we assume a normal probability distribution for a continuous random variable for such things as heights and weight of people, then we would want to find the probability that someone might be between two values where A and B are real numbers and find the area corresponding to the normal curve from A to B. If a normal probability distribution is used to approximate a binomial probability distribution, then we find P of A, X is between A and B, where A and B are non-negative integers by finding the area under the corresponding normal curve, A minus 0.5 and B plus 0.5. So this is only when we're doing between. So I'll show you how to adjust this if you're doing less than or greater than in just a minute. But so if you're doing a binomial, so say our binomial is supposed to be measuring from 5 to 8, when we make the normal adjustment and use that, we have to take a half step back from this one and a half step forward on this one. And the reason for that is if we don't, we won't get the full bar of the histogram. So I'm going to visually show you that on this example we're going to look at. Okay. So this is the key thing, is changing the adjustment of that number value first before you convert it to a z-score. Okay. So let's look at this. It says a credit card company claims that their card can be used by 40% of the people buying gasoline in a particular city. Notice that is a percent, they didn't give you a mean or a standard deviation. They said there's a percent of success. So success is measured by someone using their card, and they gave us a P, a probability of success of 0.4 if we turn that 40% into a decimal. So that means not using the card is the other option. Either someone uses the card or they don't use the card. Those are the only two options when this company did their research. So they're either tracking, did someone use our card or did they not use it? So that means 60% of the customers, people buying gasoline in a particular city, would be people who are not using that credit card company. Okay. Then they did a random sample of 20 gasoline purchasers. So that is our N. That's the number of trials, 20 people. So notice we have a percentage of success. There's only two options here. Someone either uses a credit card or they don't. And we have a number of people that they tracked. So that's our trials. So notice that if I did this I'm going to do this first by binomial over here, and I'm going to not write out all the steps. I'm going to write the generic kind of formula for you. And then I'm going to give you the answers for each of those parts. Remember, this would be me doing the formula first, doing N, choose number of successes, P, which is probability of success, to the number of successes, Q to the N minus X. I'd be using this formula for each of these probabilities. So if I have the probability that, and we're doing from 6 to 12 people. So I'm going to show you how to do it the old school way, which was binomial, using our methods from 10.4. Okay, that's what this is. And then I'm going to show you how to do this using the normal distribution, which is way quicker. Okay, so probability of, now if we're doing all possibilities between 6 and 12, that would be that our X was equal to 6, probability that our X was equal to 7, probability that our X was equal to 8, so 8 successes, 9 successes, 10 successes, 11 successes, and 12 successes. And remember, for each of these P formulas, I have to plug in the number of trials. So for the first one, maybe I'll show the formula. Actually, I'll show the formula over here to the side. This would have been 20 total people. Choose 6 people to be successful, because this is P of X equal to 6. The probability of success was people using the card was 0.4. That would be the 6 power. People not using the card is 0.6. And remember, this has to add up to 20 for the exponents. So 20 minus 6 is 14 people not using their credit card. So remember, I have to do, to get the answers that I'm about to give you, I would have to do this for each of these where the X has to change each time. So the next one would be 22, 7, and then I'd have an exponent of 7 and 13, and so on. Okay. So if I work these out using the formula, I get 0.124 for the first one, 0.166, 0.180. This is all rounded to 3 decimal places, by the way. That's kind of the standard. 0.160. Just looking at what I calculated earlier. The probability of 10 successes is 0.117. 11 successes is 0.071. And 12 successes is 0.035. And if I sum those together, I would get 0.853. Okay. So this would be using the 10.4 method. But again, I'm shortcutting a lot of this and giving you the answers. You would have to write out the correct formula for each one of those X's using this and your N and your P and Q. And you'd have to type all that into your calculator, write down the answer for each one, and then add them together. That's going to take you a lot of time. Okay. Now, visually, I wanted you to see what's going on with this problem. So to do the normal distribution, the first step is to do it with the normal. So normal approximation. And for this first one, I'm just not showing you the rule to know I can do it yet. I just want to show you the calculations. Once we get past this example, I am going to tell you the rule for how do I know I can use the normal approximation. You can use it on this one, but I will verify that for you on the next page. So for the normal approximation, what you have to first do is find the mean of your binomial distribution and the standard deviation. You need those or you can't find a z-score. So the mean, remember, is n times p. We had 20 people with a probability of success of 0.4. So that is a mean of 8. So that comes out to 8. Standard deviation for binomial distribution, this is again from our 10.4 notes, is n times p times q, but all under a square root. Let me make that a little cleaner. So square root of n p q. Okay, so that would be square root of 20 times 0.4 n times 0.6, and then I take a square root of that. Now, when I did that on my calculator earlier, I got 2.19. We typically round that to 2 decimal places, okay? Now, before you can do your z-scores, because I need a z-score for the left endpoint and to the right endpoint, because I'm doing from 6 to 12. Because that's their binomial values, look down here. So if you imagine the binomial being here, the binomial goes, remember, from 0 to the number of trials, which is 20. Now they use 0 at the y-axis, which I don't like always doing, but that's how they set these up. So they've got their histogram bars. You can see the probability peaks out at the mean right there. So that's the highest one. 8 is the mean. Notice that 6, the bar 6, actually goes further down. The histogram bar ends here, okay? And the histogram bar for 12, which is this value, it actually goes a little further than the number 12. So why we have to do those half-step adjustments is because we are adjusting from a bar graph to a nice line at that specific midpoint value of the bar. Okay, that's where the half-step adjustment comes from. So because you're going from histogram to a single line, you're off a little bit, and that's where the 0.5 adjustment comes from. So this one would be 5.5, and this one would be a little bigger. It'd be 12.5. So a little half step down, half step up. So that's how you do between. So we're going to be doing a z-score for 5.5 and 12.5, not 6 to 12. Okay. So that's our adjustment. That's called the continuity correction. So we do, remember, formula for z-score. Your item is 5.5. Your mean is 8. We just found that. Your standard deviation is 2.19. Okay. I worked that out on my calculator and I got roughly negative 1.14. We usually round our z-scores to 2 decimal places. Then I did the 12.5. So 12.5 minus 8 divided by 2.19. That's going to be 2.05. If you think about that visually, what that looks like, we're going between, and you can see it here. Part of my area is below the 0, or our mean. Part of it's above it. You can see the two different color codings here. So here's 0. Here's roughly where negative 1.14 might be. Here's roughly a little further to the right, 2.05. Our table, remember, only gives us area from 0 to a specific z-score. So I'm going to have a pink area, or whatever color you want to use, for the negative side. And I'm going to represent this side with a green area. Okay. So I need to look up 2 separate values in my table because I'm going below and above the mean. I'm going on both sides of 0. Okay. So I'm going to be doing the probability from 0 to negative 1.14. So we just need to look up, remember, 1.14 because the areas are symmetric from 0. Okay. So 1.14. So 1.1, 0.04, find that one. That's 0.3729. So this area right here, 0.3729. Now I'm going to look up the green area. That's to 2.05. So 2.0 and then 5 as the second part of the decimal. Find where those overlap. 0.4798. So 0.4798. I want the area between the 2 endpoints. So I want to add my pink and my green. So 0.3729 plus 0.4798. That equals 0.85. It rounds to 853, but if you add it right now, let's see, that's 7. Carry the 1. It's 8527. That's the actual normal approximation. Notice when we did the binomial formula, we got 0.853, but notice this rounds to that. So that's why the normal approximation is a great way, if you're allowed to use it, to get away from having to do, 1, 2, 3, 4, 5, 6, 7 different formulas of the NCX, PX, QN minus X. Okay. So if you know you can use this, you just need to find the continuity correction for each endpoint, the z-score for each of those, and then look them up in the table. Okay, so we're going to do one more with this same example, kind of a little different question though, which direction we go. But I want to show you again how the normal distribution can be used to find this quicker. So we want to do fewer than 4 people. So that means less than 4. That means not including 4, because they did not say at most 4. Fewer than 4 means less than 4, okay? So it's not including the 4. So if you think about the picture down here, again, 8 is the mean, right? 4 is right here, but we don't want to include 4. So we're actually just doing bars 3 and down. So notice bar 3 actually is a little bit, here's the 3, there's the number 3, it's in the middle of the bar. But we go a little bit higher than that to finish bar 3. So notice it's a half step above where we're going. So we're doing 3.5. So my z-score is a 3.5. So I'm doing the item, which is 3.5, minus the mean, which is 8, over 2.19. Same mean and standard deviation. We're doing the same setup. This equals negative 2.05. Now, again, you have to be careful. The area that we're finding this time is we want to be less than that because we want to go to negative infinity. Okay, so when we look at this, we're doing the area below this. So this is, again, make sure you know how to read your table. The table is going to give you this area in between. We want to do half of the bell curve, which is 0.5, minus the table value, gives you that little tail on that one side. Now, we already looked up 2.05 just a second ago. We just had a positive version of it. It was an area of 0.4798. So this is 0.5 minus 0.4798, which equals 0.0202. Now, for this next example, I'm actually going to skip down and tell you the rule of thumb test first before I do this, because I want to show you that we can check it before we actually do this problem. So it says, and essentially this is just when are we allowed to use the normal distribution as an approximation for binomial. So it says, considering that a normal distribution provides an adequate approximation for binomial distributions for large values of n, the question becomes, what is a significantly large value of n? The following rule of thumb provides a good test. Use a normal distribution to approximate your binomial distribution only if the interval mean minus 3 standard deviations to mean plus 3 standard deviation lies entirely in your interval from 0 to n. So let me explain what they're doing here. So let's look at this example. So it says a credit card company claims that their card can be used by 40% of the people buying gasoline in a particular city. Okay, so remember that's our P, 0.40. Our Q then would be 0.60. A random sample of 20 people. So again, this is the same problem. 20 people can be used to purchase, made purchases. If the company's claim is correct, use the normal curve to approximate the probability that the sample is. Now, usually we will tell you to use the normal curve, but I want to show you why I know it's okay. So what they told us we can do is you have to find your mean for your binomial, which we're going to have to do anyway. So mean is always, remember, n times p if you're binomial. So 20 people times 0.4, we know that that's 8. Standard deviation is square root of NPQ, which is square root of 20 times 0.4 times 0.6. We just did that one a minute ago as well. We know it's 2.19. So how you find this interval right here, because they've already given you the answers for it, we take and do our mean minus 3 of our standard deviations. So that's just tripling, so making it like doing it 3 times. And then we do the mean plus 3 of our standard deviations. That's how they find that interval. Okay, so that's where they got the numbers 1.43 and 14.57. So notice that is the value for 1.43 is the value for the first part, and then 14.57 is the value for the second part. As long as this interval is completely between 0 to n, my n was 20 gasoline users. So this is completely inside the range of 0 to 20. Okay. If that is true, you are allowed to use the normal distribution for your binomial. Okay. Different textbooks have different way of verifying that that's allowed, but this is how the finite book uses it. Okay. So if I'm doing from 5 to 9 users, that would be, remember, a continuity correction. We need to go a little bit below the 5 to make sure we include the 5, because they did say from 5 to 9. We're going to go a half step above 9 to make sure we fully get the 9 histogram bar. So that'd be 9.5. So a half step down and a half step up when you're doing between. And then we find those z-scores. So it's 4.5 minus 8, because we already found that mean down there. Standard deviation was 2.19. This is a z-score of negative 1.60. For 9.5, we do 9.5 minus 8 divided by the 2.19. That's going to be 0.68 when you round it. Okay. So again, visually, what are we doing? Here's our bell curve, 0. We got going down to negative 1.6 and going up to 0.68. Notice we are on both sides of 0. When you're on both sides of 0, you kind of think of it as two separate areas that we're going to add together. So we're going to find the area using our table from 0 to 1.6, because remember, they don't have negatives on the table, and then from 0 to 0.68. So for the 1.6 one, delete out my other information. So 1.60 is just going to be this first number in this column, so 0.4452. That's this one. And then for the blue one, 0.68 is going to be 0.6, 0.8, 0.08, I should say. So if we follow that over, that's going to be 0.68. So that's a 0.2517. Okay. So 0.2517. To get the area between both sides part, we add that together. So 0.4452 plus 0.2517 is 0.6969. So there's that probability. Okay. All right, now we're doing more than 10 users. So again, sometimes you have to think about what your picture looks like. More than 10 would be a histogram where we have a 10 and then we keep going up to 20, right? All the way to whatever 20 looks like. Well, to get from 10 and above, you actually have to start at the beginning of that histogram bar. So you're actually going down a half step from your center of 10. So that's a 9.5. So when we do greater than 10, that's going to convert using our continuity correction to greater than 9.5. Okay, because that way we get the whole 10 histogram bar. So you do have to sometimes think about that. Now I need to have room to draw it. Okay, so z of 9.5 is going to be 9.5 minus 8 over 2.19. So when we do that one, we've got, for some reason, I didn't have this one worked out on my notes. We have 9.5 minus 8 is 1.5 divided by 2.19. And that's going to be 0.68. Oh, obviously I didn't work it out because I had it right above there. So notice this time though, when we draw the picture of what we're doing 0, and here's the 0.68. We're going to get this value from the table, which I already have looked up. We're wanting the area to the right of that. That's what we're wanting this time. So we're going more than 10 users, so 9.5 and above. So we're going to be having to do 0.5 minus the table value. Okay. Now I already looked up the table value for this part. So actually, did I do this right? More than 10 users. Back up. Erase. More than 10 means we're actually doing bigger than 10. Does not include 10. That's why that didn't look right. So it does not include 10. Sorry about that. That is my fault. So let's redraw that histogram bar part, because that is going to change this value right here. Okay. So imagine having the 10 histogram with the 10 in the middle, and then you have 11. So again, I'm just estimating what these bars might look like. And then that goes all the way down to 20. So we had 20 gasoline users. We want more than 10. I was drawing it at the wrong spot. More than 10 means we actually want to start at the 11 bar. We're counting 11 people or more. So this is where more than 10 would hit off. So that's actually a 10.5 for that halfway mark. So we're doing a z-score of 10.5. My bad for that. And so that would be 10.5 minus 8 over 2.19. That gives me a z-score of 1.14. So we're doing 1.14. Okay, so I will have to look that up in the table. So 1.14 is 1.1 0.04. We find where those two overlap. That's 0.3729. So this part right here, the table, gives me 0.3729. So I would do 0.5 minus that to get the area to the right of it. This keeps wanting to zoom out. And that's going to be 0.1271. There we go. Okay, so we already talked about the rule of thumb. So now we're on our last page. This is the last page of notes. This is just more examples showing you how to do this process. So it says a company manufactures 50,000 ballpoint pens each day. The manufacturing process produces 50 defective pens per 1,000 on average. So even though that's not a probability as a percentage, it is a probability of as a fraction. So we're considering, so let's see, the process produces 50 defective pens per 1,000, a random sample of 400 pens. So the random sample is your N. That's the experiment. That's the number of trials from each of those days' productions and tested. What is the probability that the sample contains at least 14 and no more than 25 defective pens? So we're considering defective pens being kind of a success here, which is kind of weird, but they're saying we're counting how many defective pens we have. So that's our success. So if we get a defective pen, that's considered a success, which means if we don't get a defective pen, we have a failure, okay? Because they're looking for defective pens. So the probability of success is, now they told us that, it's 50 out of every 1,000 are defective. So I would turn that probably into a decimal. That would be 0.05 if we divide that. So that means that if I'm 5% of the time I'm defective, 95% of the time my pens are not defective. Okay, so there's my N, my P, and my Q. Now, I do not want to do this NCX formula, the binomial distribution formula, for all the values between 14 and 25. That'd be a lot of calculations. So we want to do this using the normal distribution. So let's check it. The mean is needed first. So the mean is how many items we have times the probability of success, which means getting a defective pen, and that equals 20. The standard deviation is the square root of the number of trials times the probability of success times the probability of failure. I rounded that big answer to 2 decimal places, which is 4.36. Now, they didn't tell me here that I could use the normal distribution. Like, they didn't say it in the directions. They didn't say use the normal distribution to do this. So I would probably check the rule of thumb real quick. We don't do that to you on the test. It actually says use the normal distribution. So rule of thumb, we have, remember, you take your mean minus 3 standard deviations to the mean plus 3 standard deviations. And as long as this interval is between 0 to n, so 0 to 400, that is our interval for 0 to n. As long as these numbers are between 0 and 400, we can use the normal distribution. The lower one is 6.92, and the upper one doesn't even get much bigger than that. It's 33.08. So notice this interval is within a 0 to 400 range. Okay, so that's the rule of thumb. That's how I know I'm allowed to use the normal distribution. Okay, so when we look at this from at least 14, that means we include 14, to 25, no more than. So it's okay to have 25, just no more than that. We're doing inclusion on both of those. So that means we need to do a z-score of 13.5, a half step down to make sure we get the whole bar of 14, and a half step up on 25, so 25.5. Always with the between ones, if you're including the endpoints, it's a half step down and a half step up on the endpoints. The lower one is the half down. The upper endpoint is the half step up. So we're going to do our formula. So 13.5 minus the mean of 20 that we came up with, divided by the standard deviation of 4.36. That gives you a z-score of negative 1.49. And then we have 25.5 minus 20 over 4.36. That gives me a a z-score of 1.26. Think about my picture, what that looks like. Here's 0 in the middle, going down to negative 1.49, going up to 1.26. Again, just rough estimating where I think those are. That's two different sides of my 0. So I'm going to have to do two areas from my table. 0 to the one side and then 0 to the other side. Okay, so I'm going to look up 1.49 first. Let's get rid of some of this extra stuff. Just helps to, on the test, feel free to write all over your table that I give you. So 1.49. So 1.4, and then over here at 0.09, and that row is 0.4319. So this area right here is 0.4319. Then we need the area from the 0 to the 1.26. So 1.2, 0.06. Find where those two overlap. That's going to be 0.3962. So this side over here is 0.3962. Since we're doing between, we add those together to get our approximation. And that gives me approximately 0.8281. About 83% almost. Okay. They just said probability though, so I don't need to convert it to a percent. All right, what about 33 or more defective pins? Okay, so this time they are including, because they said 33 or more. So greater than or equal to 33. Again, think about where that 33 bar is. You're actually including 33 this time, so we need to shade 33 and everything above it. So we are going to step down to 32.5. We want to make sure we include the whole bar of 33. So my z-score is going to be 32.5 minus 20 over 4.36. And that gives me a rough z-score of about 2.87 when I rounded it. Draw a picture of what that looks like. Here is 0. Here is roughly 2.87. It's going to be close to the end of the curve. And then we want the or more. That means greater than or equal to, right? So we are looking at the area above this little mark, okay? So remember, our table will tell us this. We do 0.5 minus the table if we're just getting the top half of a tail on one side. Okay, so if we look up 2.87, so 2.8 is a little further down, and we got to find 0.07, which is this column right here. So 2.07 is going to be 0.4979. So 0.5 minus 0.4979 is going to be approximately 0.0021. Now, this last example is almost identical, so I'm just going to write it up in the ink before I post the video or the note in the videos. So we're going to end the video here just because you already have lots of video content to watch anyways because of the missed class on Thursday. But this ends up the 10.5 notes. I will write this one in ink. So you can try it on your own first if you want to, and then look at my ink notes to see if you did it correct. I hope you have a wonderful day.